Hello, this is the lecture PowerPoint for Chemical Equilibrium, Chapter 15 of the Chang textbook. And what we're looking at here on the left picture, introduction to the chapter, is that we have our skier over on the left, and that's representing how you can have various phases in equilibrium, phases of matter. And over here on the right, notice how we have the molecules in our liquid, but they're going out into the gaseous form. But look at that equal arrow coming back into our liquid form. That is what we mean by equilibrium. So on slide 2, equilibrium is a state in which there are no observable changes as time goes by. Your biological term for this is homeostasis. Chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. Over on the right here, this physical equilibrium. Again, what we saw in that first slide, we had water in the solid form, the liquid form, and then in the gas form, and they were all in equilibrium on that nice day. On an equilibrium, a chemical equilibrium, and this is the one where we're going to talk about in depth, this reaction, is when you have N2O4 being converted to NO2. And so NO2, a nice orangish gas, but we're going to peek at the N2O4, a brownish gas, and see how these two gases can be at equilibrium and what color that would actually be. Let's remember, this is one of the key concepts of the chapter is at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. On slide 2, again, here's that all-important N2O4 reaction. N2O4 is a light brown gas, and what we see here are the lighter particles in our picture. When over time, so as time increases, what will happen is this will just start to decompose into NO2, which is our darker brown gas. And so that's why our concentration of our darker brown gas, our NO2, is starting to increase. As we, again, more time increases, we get this. But at time D, eventually, there's an equilibrium established, whereby there is no change in this process.
Ampules containing nitrogen dioxide in equilibrium with dinitrogen tetroxide are put in different temperature baths: ice water, room temperature water, boiling water, and dry ice acetone. Observe the color of the ampule in each bath.
On slide 4 then, let's look at some graphs of this experiment, the NO2, N2 system at room temperature. Again, over time, we see a decrease in this top left graph of N2O4 and an increase in our product. But as time, and what we see over time is that there actually are some constant levels. These graphs over at a certain amount of time, both of these graphs plateau. And then what we see, we can measure them, these concentrations of our two gases. So here in table 15.1, again, let's look at each line of the experimental data. We have NO2 and N2O4 concentrations. And then what else we're looking at here is as our data continues here, we have NO2 concentration divided by N2O4. But eventually what we see is that when we look at a ratio of the concentrations at equilibrium, what we see is that it's all one rate, this rate doesn't change. So again, what we had were our initial concentrations of NO and N2O4, but over time these concentrations will change. And so if we take a ratio of NO2 over N2O4, no observable constant. However, If you take NO2 raised to the power of 2, we do, divided by the concentration of N2O4, we do get a equilibrium constant. So again, that's a very important idea.
Consider the chemical equilibrium between dinitrogen tetroxide, N2O4, a colorless gas, and nitrogen dioxide, NO2, a brown gas, at 25 degrees Celsius. Analysis of data for this equilibrium shows that although the ratio of the concentrations of NO2 to N2O4 gives scattered values, the ratio of the concentration of NO2 squared to the concentration of N2O4 gives a nearly constant value that averages 4.63 times 10 to the minus 3. K equals the concentration of NO2 squared divided by the concentration of N2O4, which equals 4.63 times 10 to the minus 3, where K is the equilibrium constant for the equilibrium at 25 degrees Celsius. Note that the exponent 2 for the NO2 concentration in this expression is the same as the stoichiometric coefficient. To convince yourself that the above equilibrium expression holds, no matter the starting concentrations, choose to start the reaction with pure NO2, pure N2O4, or a mixture of NO2 and N2O4. Starting with 0.670 molar N2O4, the reaction proceeds toward equilibrium with some N2O4 molecules breaking apart to form NO2 molecules. At equilibrium, the concentration of NO2 is 0.0547 molar, and the concentration of N2O4 is 0.643 molar. Calculating the equilibrium constant, K, we find K equals 4.65 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant. Starting with 0.200 molar NO2, the reaction proceeds toward equilibrium with NO2 molecules combining to form N2O4 molecules. At equilibrium, the concentration of NO2 is 0.0204 molar, and the concentration of N2O4 is 0.0898 molar. Calculating the equilibrium constant, K, we find K equals 4.63 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant. Starting with 0.430 molar NO2 and 0.300 molar N2O4, the reaction proceeds toward equilibrium with some NO2 molecules combining to form N2O4 molecules. At equilibrium, the concentration of NO2 is 0.0475 molar, and the concentration of N2O4 is 0.491 molar. Calculating the equilibrium constant, K, we find K equals 4.60 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant.
Let's look at how did this happen on slide 5. How did we know to square the concentrations of the NO2? Look at the coefficients. This is different from kinetics in that with equilibrium, you will look at the coefficients. If you recall in kinetics, you had to determine that rate order independent. So what our suggestion here is on slide 5, when you're trying to determine a rate constant, is start with NO2. Start with our NO2. And again, here is our point on our chart where we have our equilibrium. If we start with N2O4, what we will get is eventually we will get our NO2 and our N2O4 formed. So again, this straight line up where we see the concentrations of our product and reactant have leveled off, that is where our equilibrium position is. If we started way over on the right with both NO2 and N2O4, what you see is it does not take long to get to our equilibrium position. On slide 6 again, what we will look for then is notice how we now have switched. We still have K, a constant, but it is a capital K. In equilibrium, we use a capital K to denote equilibrium constant. And again, notice it is what we've been used to doing with our enthalpy and with our free energy, etc. You're going to put the products, and this time over the concentration of the reactants. But pay attention to those coefficients. That is the concentration of the product raised to the power of that coefficient, divided by the concentration of the reactant. And again, from our earlier chart or table, we saw that that K is 4.63 times 10 to the minus third. So for any equilibrium reaction, little a being the coefficient, capital A being the compound, big B the compound, and then our products C and D, and again the small letters being those coefficients, what we will have is the equilibrium constant is equal to the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. This is called the law of mass action. On slide 7 then, let's look at, explore this equilibrium constant further with our reaction. And what we will need to remember here, if K is a lot larger than 1, what will the equilibrium do? If K is larger than 1, meaning that should make sense mathematically. That means that when you divided the products over the reactants, what we will see is that you have the shift to the products, a shift to the right. If your numerator is going to be, give you a number that would be greater than, numerator divided by denominator would give you a number greater than 1, that means favor the products. If you have here, and so this is what you would have, is the reactants down here on the lower left. If K is a lot greater than 1, what we would see is a large amount of product formed. If K is a lot less than 1, then what that means is that your products, this number, the numerator, must have been smaller than what we had in our denominator. And so that means that the concentration of those reactants is going to influence this equilibrium. The equilibrium will lie far to the left, which means we will favor reactants. Now, this is important for chemists to know because they need to know how to tweak a reaction. How can I make more product is usually the favorable outcome. But what if there is a situation where we want to favor reactants, then you would definitely change those concentrations. So again, the reactants in our second scenario would be at much higher levels than our products. Homogeneous equilibrium on slide 8 applies to reactions in which all the reacting species would be in the same phase. Like our known example here of N2O4 was in the gaseous phase, and so was NO2. This is the important concept then. Then what we call it, if you have a homogeneous equilibrium, is Kc, is that it's going to have the same phase. And again, please remember that you're going to take the concentration of the product raised to the power of its coefficient divided by the concentration of the reactant raised to the power of its coefficient. Now, what about the fact that they were both gases? Can't we do something with pressure? And remember way back Dalton's law of partial pressure? Well, that holds true here with equilibrium, is that you can now also, if all your reactants and products are gases, you can solve for a Kp. And a Kp is, rather than having these concentrations in molarity, what we can do is look at pressures. And so we can solve an equilibrium constant, a Kp, if everybody's a gas, by taking the products, and in this case, the pressure pardon me, the pressure squared, and divide that by the pressure of your reactant, in this case the N2O4. In most cases, Kc does not equal our Kp because, again, look what you're doing, your pressure versus concentration. So Kp, this is a very important equation to keep track of here now. Kp is equal to Kc, so that's your equilibrium constant. Kp is your equilibrium constant of pressure. How would you solve for this? Well, you look at R, and R is our usual gas law constant this time, 0.0821, and our temperature, of course, in Kelvin, and raised to the power of the delta N, meaning your change in moles. So delta N is the moles of products minus the moles of reactants, your change in moles. And so what you would look at here is if everybody was a gas, as they are in this sample equation here, we would take the coefficients of C plus D minus the coefficients of A and B because those would be the moles of gas. On slide 9, homogeneous equilibrium continued. Let's look at an example where you take acetic acid and water and you get that acetate ion and hydronium ion. Well, Kc prime is going to be equal to, let's take a peek, is that it's going to be equal to the acetate ion times the concentration of the hydronium ion divided by the reactants, our acetic acid and our water's concentration. Now, in these problems, the water concentration is going to be constant. So if it's constant, we can actually drop it out of the expression. And so Kc is going to be equal to still the products, the concentration of the products raised to the power of their coefficients over the concentration of the reactant. And again, that's all going to be equal to that Kc prime times water. In general practice, it is general practice not to include the units for equilibrium constant. All right, let's work a problem then on this. On slide 10, example 15.1. Write expressions for Kc and Kp, if applicable, for the following reversible reactions at equilibrium. So we have our HF and water, we have our NO and oxygen, and our acetate with our ethanol. Our slide 11, our strategy. Keep in mind the following facts. Kp can be only for gaseous reactions, and the concentration of the solvent, usually water, does not appear in an equilibrium constant expression. On slide 12 then, our solution for part A. Again, here was our reaction, and we did not have all gases. Because there are no gases, you can't do Kp, so you can only calculate Kc. And so remember, it's the concentration of the products raised to the power of their coefficients over the concentration of the reactants raised to their power of coefficients. Now, HF is a weak acid, so the amount of water consumed is negligible compared with the total amount of water present. So again, we can rewrite the equilibrium constant and make our lives easier to solve by dropping out the water expression in the denominator. On slide 13, let's look at solution B. In solution B, we do need to write both a Kc and a Kp because all our reactants and products were gases. The expression is the same. Take the concentration of the products raised to the power of their coefficient divided by the concentration of the reactants raised to the power of their coefficients. Kp, how do we do that? Take the pressure of our product raised to the power of its coefficient divided by the pressure of the reactants raised to the power of their coefficients. In letter C, when we had our acetate and ethanol, which would lead to our CH3COO-C2H5 and water, the equilibrium constant we don't have gases, so we would just solve for Kc, and we would have the products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients. But again, water produced is negligible compared to the water solvent, so the concentration of the water does not change, and you just drop the water's expression out, so we would take the concentration of just our one product over the concentration of our two reactants. On slide 14, let's look at example 15.2. The equilibrium constant, Kp, for the decomposition of phosphorus pentachloride to phosphorus trichloride and molecular chlorine is found to be 1.05 at 250 degrees Celsius. If the equilibrium partial pressures of PCl5 and PCl3 are 0.85 atm and 0.463 atm respectively, what is the equilibrium partial pressure of the chlorine at 250 degrees Celsius? Our strategy on slide 15, take the concentrations of the reacting gases were given in atm, so express the equilibrium constant in Kp. From the known Kp value and the equilibrium pressures of the PCl3 and PCl5, we're going to solve for the pressure of the chlorine. On slide 16 then, the solution, first we write Kp in terms of partial pressures of the reacting species. So Kp is going to be equal to the pressure of the PCl3 times the pressure of the Cl2 divided by the partial pressure of the PCl5. And substituting in the values that were given in the problem, okay, we're going to get, substituting our values in, this was our unknown, PCl2, so rearranging and solving for that, we get the partial pressure of the chlorine to be 1.98 atms. On slide 17, let's check that. We have added atmospheres as a unit for PCl2 because they were asking for a pressure. Example 15.3 on slide 18. Methanol is manufactured industrial by the reaction of taking carbon dioxide and water to make methanol gas. The equilibrium constant for the reaction is 10.5 at 220 degrees Celsius. What's the value of Kp at this temperature? Example 15.3 solution on slide 19, our strategy. The relationship between Kc and Kp was given by that equation 15.5. Remember, what's the change in the number of moles of gases from reactants to product? Again, you're going to calculate delta N, the moles of the gaseous product minus the moles of the gaseous reactants. And again, we should use Kelvin. On slide 20, the solution then, this is our equation to keep track of. Kp is equal to Kc times RT raised to the power of delta N. So they gave what we're looking at here then, Kc is equal to 0.0821. We should probably have some labels here, liter atmosphere over mole Kelvin. And then we're going to have our temperature in Kelvin, and then we'll calculate delta N. So what we saw is, again, here is our Kelvin temperature. Here's the moles of our products minus the moles of the reaction. So yes, delta N is a negative value. You're going to take 10.5 times 0.0821 times 473 raised to the power of the minus second. Please try that on your calculator so you can see you would come up with 6.41 times 10 to the minus third. Check this on slide 21. Note that Kp, like Kc, is a dimensionless quantity, so kind of strange not to have labels. But this shows we can get quite a different value for the equilibrium constant for the same reaction, depending on whether we express our concentrations in moles per liters or use those partial pressures and express our answer in atmospheres. Heterogeneous equilibrium on slide 22 applies to reactions where the reactants and products are in different phases. And what you're doing is looking at a reaction quotient for a heterogeneous system that's only going to depend on concentrations that change. So let's look at that as we look at this problem. Calcium carbonate is a solid, and it will eventually decompose to give you calcium oxide and some CO2 gas. Now, Kc, you would think, is going to be the products, is going to be equal to the products raised to the power of their coefficient times the other products divided by the concentration of the reactants raised to the power of its coefficient. But notice the phases. We have two solids, and so our calcium carbonate and our calcium oxide concentrations are constant. Therefore, Kc is just going to be equal to the concentration of the CO2, which again would be equal to Kc prime times the product, um, K, rearranging here, and you would get concentration of calcium carbonate over the calcium oxide. However, Kp would just be simply equal to the partial pressure of our CO2. So the concentration of solids and pure liquids are not included in the expression for an equilibrium constant. On slide 23 then, looking at this reaction again, here's what it would look like. Here's your calcium carbonate, the red, and here's our calcium oxide, and there's our gases CO2. And what you see here is that over time, you may have a switch in our amounts of red and green here. However, what really is going to change is going to be the pressure due to the carbon dioxide. So the partial pressure of the carbon dioxide is going to be equal to Kp. And what you see then is that difference in your mercury levels is what they're pointing out here, is going to be what you measure for your equilibrium expression. So take that your change in height of mercury. Partial pressure of CO2 does not depend on the amount of your solids, your calcium carbonate or your calcium oxide. Slide 24, example 15.4. Consider the heterogeneous equilibrium then of calcium carbonate going to calcium oxide and CO2. Here's your data. At 800 Celsius, the pressure is 0.236 atmospheres. First calculate Kp and then Kc at this temperature. On slide 25 then, let's remember, our arrows there, our calcium carbonate is going to decompose, but you have pure solids that do not appear in the equilibrium expression. So the relationship between Kp and Kc is going to be that equation 15.5 again. And using equation 15 along with that, then that reduces down to Kp is going to be equal to the partial pressure of our CO2, and that would be 0.236. From equation 15.5, remember Kp is equal to Kc times our gas law constant times our Kelvin temp raised to the power of our change in moles. Well, our change in moles here is 1. It went from 1 minus 0, so that's going to be 1. And so Kc is going to be 2.68 times 10 to the minus third when we substitute in our values. On slide 27, let's look at A and B reactants going to C and D, and then a two-step process whereby C and D were those intermediates that are going to turn into new products, E and F. So again, back to our Hess's law where we're going to combine some equations. So now what would our equilibrium expressions be? Well, for Kc prime, the first one, it would be products raised to the power of their coefficients over reactants. And for Kc2, it would be those products divided by the concentration of the reactants. What happens then is just like what happened in Hess's law is you see that these products of the first reaction that became the reactants are being crossed out. So when you bring down like species that were crossed out, you get A plus B equals E plus F. Therefore, the equilibrium expression would be Kc is equal to the concentration of the products raised to the power of their coefficients over the concentration of the reactants raised to the power of their coefficients. Now, Kc should be equal to Kc prime times Kc2 prime. And if a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall is given by the product. You multiply the equilibrium constants of the individual reactions. Let's go back to our equation of N2O4 gas changing to NO2. And what about the reverse, N2O changing into N2O4? Well, the equilibrium expression for the first one we knew was equilibrium constant was 4.63 times 10 to the minus third when we took the concentration of the NO2 raised to the power of its coefficient over N2O4. K prime would be N2O4 divided by the concentration of NO2 raised to the second power. Well, that should be equal to 1 over K then. And so it should be 2.216. So when the equation for a reversible reaction is written in the opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. So on slide 29, writing equilibrium constant expressions, let's summarize. The concentration of the reacting species in condensed phase are expressed in molarity. In the gaseous phase, you have two options, molarity or ATM, or these partial pressures. Number two, concentration of pure solids, pure liquids, and solvents do not appear in equilibrium constant expressions. Number three, the equilibrium constant is a dimensionless quantity. Number four, in quoting a value for the equilibrium constant, you must specify the balanced equation and the temperature. And number five, if a reaction can be expressed as the sum of two or more reactions, then the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reactions. On slide 30, continuing our discussion of chapter 15, let's discuss chemical kinetics relationship to chemical equilibrium. Let's say we have a reaction where A and 2 moles of B are going to form AB2. We would look at the rate constant of the forward reaction going towards the products. Reversing this towards the reactants, we would find the rate constant reverse. The rate forward is going to be equal to what we learned in our work so far is the rate constant times the concentration of A times the concentration of B raised to the second power, that coefficient, versus the rate of the reverse is going to be equal to the rate constant reverse times that concentration of our product, AB2. Equilibrium. In equilibrium, what we're saying is the rate forward equals the rate of the reverse equation. So if that's the case, rate forward is K times AB squared is equal to K reverse times AB2, the concentrations. Let's solve for KF over KR. And so what that would give us is the expression called KC, big KC, which is now the concentration of the products over the concentration of the reactants raised to the power of their coefficients. On slide 31, the reaction quotient, QC, this is called a reaction quotient, is calculated by substituting the initial concentrations of the reactants and products into our KC expression. So if QC, this is the reaction quotient, is less than our equilibrium expression, then what's going to happen is we're going to get more, the equilibrium is going to shift from the left to the right. We're going to get more products. Now this should make sense since QC is the concentration of the products over the concentration of the reactants. And so it should make sense then that having QC be less than KC would give us this situation of more products. If QC equals KC, then what we have is equilibrium, no net change from forward or reverse. However, if QC is greater than KC, what's going to happen is we're going to favor the reactants, is that the reaction will shift from the right to the left towards those reactants, and we will make more reactants than products. On slide 32, example 15.5, at the start of a reaction, there are, let's look at all our numbers now, 0.249 moles of nitrogen gas, 3.21 times 10 to the minus second moles of hydrogen, and 6.42 times 10 to the minus fourth moles of ammonia, all in a 3.5 liter reaction vessel, and our temperature is 375 Celsius. If the equilibrium constant for Kc for this reaction is 1.2 at this temperature, Decide whether the system is at equilibrium, and if not, predict which way the net reaction will proceed. So again, this is our balanced equation. Let's see, are we going to favor our reactants? Are we going to favor our products? Or is it just going to be all at equilibrium? On slide 33, then, our strategy, we are given the initial amounts of the gases in moles and in a vessel of known volume, liters, so we can calculate moles per liter, which is our molar concentration, and that would give us our QC. How does a comparison of QC with KC enable us to determine if the system is at equilibrium, or if not, which direction will the net reaction proceed to reach equilibrium? That was what was on our previous slide. So our solution on slide 34, the initial concentrations of the reacting species, let's just do moles over liters, 0.249 moles over 3.5 liters would be 0.0711 molar for the N2O, and again, the O means initial. The initial concentration of the hydrogen, take your moles divided by liters, you get 9.17 times 10 to the minus third. For ammonia, 1.83 times 10 to the minus fourth molar. On slide 35, then, write QC. QC for this equation again, remember, what you're going to do is take the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Substituting your values in, you should get 0.611. Now that's QC. Now remember, it said Kc was 1.2. Therefore, Qc is less than Kc. And so the system is not at equilibrium. The net result then would be an increase in the concentration of the ammonia, meaning we're going to strongly shift towards our products, and a decrease in the concentration of the reactants. That is, the net reaction will proceed very strongly from left to right until we do get our equilibrium. On slide 36, how do we calculate equilibrium concentrations? Number one, first express the equilibrium concentrations of all species in terms of initial concentrations and a single unknown x, which represents the change. Number two, we write the equilibrium constant expression in terms of equilibrium concentrations. Knowing the value of the equilibrium constant, we're going to solve for x. Then, having solved for x, calculate the equilibrium concentrations of all species. Example 15.6 on slide 37. Here's your data. 0.5 moles of hydrogen, 0.5 moles of iodine were placed in a 1 liter stainless steel flask, 430 degrees Celsius. The equilibrium constant for Kc for this reaction of H2 plus I2 yields 2HI is 54.3 at this temperature. Calculate the concentrations of hydrogen, iodine, and our hydrogen iodide. On slide 38, here's our strategy. Looking at our problem, we're given initial concentrations of the gases in moles and the volume in liters, so we can again calculate the molarity. Because initially no HI was present, the system could not be at equilibrium. You haven't made any yet. Therefore, some H2 would react with the same amount of I2, okay, to form HI until the equilibrium was established. Again, how do we know the same amount? Look at those coefficients. It's a 1-to-1 ratio. So on slide 39, then, the solution. Follow the preceding procedure to calculate concentrations, and that is, look at that stoichiometry. There was 1 mole of hydrogen reacting with 1 mole of iodine to give us 2 moles of HI. What we're going to build here, folks, is called an ICE table. You can see how it's ICE, I-C-E. What are our initial concentrations? What is our change? And what will be our equilibrium concentrations? So again, what the previous slide said is X is the depletion in concentration of the molarity of H2 and I2, meaning you start your reaction and you're going to deplete the amount of H and I, and it is equal because it was a 1-to-1 mole ratio by the same amount. It follows then that the equilibrium concentration of HI must be 2x, and notice we put the plus sign, plus 2x. So we summarize this again. Here is what you do. On the first line, you write your balanced equation. Here we have H2 plus I2 yields 2HI. And then on the second line of the table, you write your initial concentrations. Remember, it was 0.5 molar. Notice how we don't use our labels here because they're right here. It was 0.5 in a 1 liter container, so 0.5 molar for the hydrogen and the iodine. And initially, again, we have no HI. The change, again, it's minus X and minus X for our iodine and our hydrogens because of the 1-to-1 mole ratio. It's a plus 2X for our HI. So now add these two lines together. And so you get 0.5 minus X is going to be the concentration of the H2. 0.5 minus X for the I2 equilibrium concentrations now. And 2X is going to be our concentration of the 2HI. On slide 40 then, substitute this, what you just solved for, or what we know as our equilibrium expression, would be the product of the products raised to the power of their coefficients divided by the product of the reactants raised to the power of their coefficients, their molarities. So they gave us Kc, 54.3. Again, remember that concentration, equilibrium concentration of HI from our table was 2X, and remember to square that. Our denominator would have the concentration of HI and I2 at equilibrium, which is 0.5 minus X and 0.5 minus X. Now, how are you going to solve this equation? How are you mathematically do you solve it? Well, what you do is take the square root of both sides. When you have these obvious values, this is 0.5 minus X squared, right? So, and you have 2X squared up here. When you have a problem that looks like this, take the square root of both sides. So the square root of 54 is 7.37. The 2X squared reduces down to 2X, and the 0.5 is minus X is just one of those. Now, how do we solve for X? Let's do our algebra, right? You're going to multiply both sides by 0.5 minus X, and so we can get rid of that expression. And so when you finally solve this, you will get X to be 0.393. So there's quite a bit of algebra in solving these equilibrium problems. On slide 41 then, on step 3, at equilibrium then, the concentrations are, we just solved for X, 0.393. So what's hydrogen? We said it was 0.5 minus X, so 0.5 minus 3.93 is 0.107. Iodine should be the same concentration, 0.107. The HI is 2 times X, we said, so it's 0.786 molar. You can check your answers by calculating Kc using the equilibrium concentrations, meaning plug all those back into the Kc expression, and remember that Kc is constant for a particular reaction at a given temperature. On slide 42, example 15.7. For the same reaction and temperature as we used in the previous example 15.6, this H2 plus I2 yields 2HI. Suppose the initial concentrations of HI, I2, and HI were all 0.00623 for the H2, 0.00414 for the I2, and the HI was 0.0224 molar. Calculate the concentration of these species at equilibrium. On slide 43 then, our strategy from the initial concentrations, we calculate the reaction quotient, QC, to see if the system is at equilibrium, or if not, in which direction the net reaction will proceed to reach this equilibrium. A comparison of QC with KC enables us to determine if there will be a depletion in H2 or I2 or HI as equilibrium is established. On slide 44, then the solution, how do we calculate QC? Remember, it's a concentration of the products raised to the power of their coefficients, and the O means initial, and divided by the concentration of the reactants raised to the power of their coefficients. Substituting the given values in, we get Kc then to be 19.5. Now we know Kc, or QC, is much, much smaller than Kc, which was 54.3. So we conclude, since Qc then is less than Kc, then the reaction will proceed from left to right until equilibrium is reached. See that figure 15.4? That is, there will be a depletion of the reactants of the H2 and I2 and a gain in the HI. On slide 45 then, we're not done yet. Now we want to run through our ICE table. Step 1, let X again be the depletion and concentration of our moles of H2 and I2 at equilibrium. Look what we're doing. We're taking our initial concentrations of H2 and I2, and this time we did have some HI in our system, so 0.0224. From the stoichiometry again, it's going to be minus X for our reactants and plus 2X for our product. Now, add these two lines together. 0.00623 minus X, 0.00414 minus X would then look like this, and 0.0224 plus 2X would be our equilibrium concentration of that product. On slide 46 then, the equilibrium constant, again, is calculated by the product's concentration raised to the power of their coefficients divided by the reactants, concentrations, substituting in our value, Kc was 54.3. These are our equilibrium expressions now. There's 0.0224 plus 2x, remember to square it. HI, a hydrogen is going to be 0.00623 minus x, hydrogen 0.00414 minus x. Now, can we take the square root of both sides? No, because look how these values are not the same. Therefore, it is not possible to solve this equation by taking the square root shortcut because the starting concentrations of H2 and I2 were unequal. Okay. Instead, we must first carry out the multiplications. So, this is where extreme algebra comes in. 54 times 0.00623 minus x times that 0.00414 minus x is going to give us 2.58, distributive property there, 2.58 times 10 to the minus fifth minus 0.0014x plus x squared, which is all going to, multiplying through then, 5.02 times 10 to the minus fourth plus 0.0896x plus 4x squared. On slide 47 then, collecting these terms, what you'll end up with is 50.3 times x squared minus 0.654x plus 8.98 times 10 to the minus fourth is all equal to 0. Now, what do we do with this? That's why we're taking Algebra 2, is we're going to use the quadratic equation to solve for this. Remember, the quadratic equation is ax squared plus bx plus c is equal to 0. So the solution for the quadratic equation, if you don't know how to do this, it's pretty slick equation right there on your graphing calculators. Go to Appendix 4, and what you would do then is rearrange, and solving for x, x would be minus b plus or minus the square root of b squared minus 4ac over 2a. So plugging in our values, and this is why we like our calculators. With our calculators, this is all we have to do is type in with the quadratic equation. A is 50.3, B is minus 0.654 up here. This is where we're getting this. And C was our 8.98 times 10 to the minus fourth. So if we want to substitute into this equation, we would solve, and x would come out to be either 0.0114 molar or 0.00156 molar. Try this on your calculator, and again, try to get that quadratic equation downloaded so it's easier to use on a quiz and test. On slide 48, those two numbers that they gave us, the first solution is physically impossible. Why? Well, because the amounts of H2 and I2 reacted would be more than those originally present. That's not feasible. So that's why when you have two positive answers, the second solution will give the correct answer. Note that in solving quadratic equations of this type, one answer is always physically impossible, so choosing a value for x is easy. Step 3 then, at equilibrium, substitute back in then the value for x into your expressions. You had 0.00623 minus x for hydrogen, so that new molarity would be 0.00467 for the iodine, that you would calculate this to be 0.00258, and for the molarity for the HI would be 0.0255 when you took 0.0224 plus 2x, and this would be your final molarity. On slide 49, check this again. You could go back and calculate Kc by using those numbers, those equilibrium concentrations, and remembering that Kc is a constant for a particular reaction at a given. Let's continue our discussion of chapter 15 on slide 50 with Le Chatelier's principle. And what we know about Le Chatelier's principle can all be summarized in a quick diagram here. And what it says is if you exert, here's your system at equilibrium. If you apply a stress, let's say you increase pressure, what the system will do is try to decrease that stress in such a way that it will partially offset the system and you will get a new equilibrium established. And just down here on the bottom, make this note, when you have this new equilibrium established, all the concentrations are changed, but the Kc will remain the same because the temperature in all of this has remained constant. So let's talk about a change in concentration in this reaction. What if you have N2 plus H2 to give you ammonia? What happens if you add ammonia? Well, what the system will do is try to decrease then the amount of that ammonia. So in order to do that, it will shift this equilibrium to the left to offset this stress. Let's take a peek at this graph over here on the right. And what happens then is, again, you took ammonia's concentration and you increased it. This was the stress applied. But now the system will try to offset that stress by decreasing the amount of ammonia. But look what happened in the meantime to the concentration of the hydrogen, one of the reactants, and the nitrogen. They both increased. On slide 51 then, Le Chatelier's principle, continuing this discussion about concentration. Now let's talk about product A and B going to C and D and looking at those coefficients, small a, small b being, and small c, small d being the concentrations. So what happens if you add more product? The system will try to make less product, so it will shift your reaction to the left towards the reactant. So an increase in the concentration of products, what happens then? You will shift your equilibrium to the left. What if you remove your products? So do the same diagram, but now go down. This is this applied stress. The system will try to offset that stress by increasing the production of the products. So decrease the concentration of the products, will try to shift to make more product. So your equilibrium will shift to the right. What if you increase the concentration of the reactants? The system will try to decrease the concentration of the reactants. How does it do it? It's going to have to shift towards the products. What if you decrease the concentration of the reactants? The system will try to offset that stress and make more reactants then. Slide 52 then, example 15.8. At 720 degrees Celsius, the equilibrium concentration, Kc, for nitrogen plus hydrogen to yield ammonia is 2.37 times 10 to the minus third. In a certain experiment, the equilibrium concentrations for the nitrogen 0.683, for the hydrogen 8.80, and the ammonia is 1.05. Again, these are equilibrium constants. Suppose you add ammonia to the mixture, so the concentration will go up to 3.65 molar. Use Le Chatelier's principle to predict the shift in the direction and then confirm your prediction by calculating QC and comparing that to our KC. On slide 53 then, the strategy again, what is the stress and how does the system adjust to offset that stress? And then in B, at the instant when some ammonia is added, the system is no longer at equilibrium. So how do we calculate QC? And then how do we compare QC to KC to tell us direction? Well, on slide 54, what we said is you're going to apply this stress by adding more NH3. To offset this stress, some of the NH3 will react and produce the nitrogen and hydrogen, and a new equilibrium will be established. The net reaction then is to shift towards the left. On slide 55 for part B, at the instant when some of the ammonia is added, the system is no longer at equilibrium. So how do we calculate a QC? Remember, it's the concentration of the products raised to the power of their coefficients, and the O means initial, divided by the concentration of the reactants raised to the power of their coefficients. Substituting in our values, our initial values, we get our QC to be 2.86 times 10 to the minus second. Then QC is greater than KC, and so the reaction will shift from the right to the left until we get QC to equal our equilibrium constant. On slide 56 again, showing this, once again, if you increase the amount of ammonia, the system will try to decrease that. What will happen is that you will increase the amount of nitrogen and hydrogen. So we qualitatively see the changes in concentration of the species in this graph. On slide 57, continuing with Le Chatelier's principle, what if we change volume and pressure? Well, let's look at our compounds and make sure that we have gases. Then volume and pressure will have an effect. So what if we increase the pressure? If you increase the pressure, the system is going to try to decrease the pressure. So what happens then? Back to our concept about moles. And the side with the fewest moles of gas will be favored. If we decrease the pressure, the system will try to increase the pressure, so we will shift our equilibrium toward the side with the most moles of gas. If you increase the volume, then the side will be favored with the most moles of gas. If you decrease the volume, this will be the side with the fewest moles of gas will be favored. So on slide 58, let's consider these three reactions, whereby you're going to react in A, some lead-2 sulfide with oxygen to give us our lead-2 oxide and SO2. B, PCl5 gas giving us PCl3 gas and chlorine gas. And C, we have hydrogen and carbon dioxide to give us water and carbon monoxide. Your job is to predict the direction of the net reaction in each case as a result of increasing the pressure, which, as we know, if P is up, Boyle's law says V is down. So what would happen with our equilibrium? Slide 59 then, our strategy is a change in pressure can affect only the volume of a gas, but not of a solid, because solids and liquids are not compressible. The stress applied is an increase in pressure. According to Le Chatelier's principle, if you increase pressure, the system will try to offset this stress and the system will try to decrease the pressure. This can be achieved by shifting to the side of the equation that has fewer moles of gas, remembering that pressure is directly related to the moles of the gas via PV equals nRT. So P is directly proportional to the number of moles. On slide 60 then, the solution for letter A. Consider only the gaseous product molecules. In the balanced equation, there's 3 moles of oxygen and just 2 moles of the sulfur dioxide. Therefore, the net reaction will shift towards the products to the right when the pressure is increased. In letter B, the number of moles of products is 2. We have 2 moles of our gas. and that of the reactants is just 1 mole of gas. Therefore, the net reaction will shift to the left towards the reactant. In letter C, the number of moles of products, gases, is equal to the number of moles of reactants. So a change in pressure will have no effect on this equilibrium. Slide 61, just double check in each case the prediction is consistent with Le Chatelier's principle. Slide 62, continuing with Le Chatelier's principle, what happens when we change temperature? Well, it depends. Let's look at the change and what type of reaction we have. If you increase the temperature in an exothermic reaction, the system will try to decrease the temperature. And so what that will do is it will cause our equilibrium constant to decrease. In an endothermic reaction, though, remember, heat then would actually be a reactant. So if you increase the heat, the system will try to decrease the heat and shift towards the right. So you will get an increase in K. So what happens if you decrease the temperature? Well, in an exothermic reaction, this will cause your equilibrium constant to increase. In an endothermic, your equilibrium constant will decrease. Let's look at, again, this reaction we looked at numerous times. When you see N2O4 forming 2 moles of NO2, N2O4 is somewhat colorless, NO2 is going towards the brownish red. When the delta H for this reaction is 58 kilojoules per mole, that means you have 58 kilojoules over on the reactant side since it was positive and it's endothermic. So again, once we shift towards our products, what will happen if you're going to try to increase the amount of heat, the system will try to decrease the amount of heat, and that means you'll try to form more product. So when it's colder, we will have our light gas. When it's hotter, when you increase that temperature, then you're going to form your brown NO2.
Ampules containing nitrogen dioxide in equilibrium with dinitrogen tetroxide are put in different temperature baths: ice water, room temperature water, boiling water, and dry ice acetone. Observe the color of the ampule in each bath.
Slide 63, Le Chatelier's principle continued here. What happens when you add a catalyst? Catalysts do not change an equilibrium constant. They do not shift the position of that equilibrium system. All it does is help that system reach that equilibrium sooner. So here's your reaction with your activation energy under the hill there. And what happens in a catalyzed reaction is that we do see that we will have a higher activation energy, but this will make the reaction go faster. Catalysts will lower EA for both the forward and the reverse reaction, but the catalyst does not change the equilibrium constant or shift the equilibrium. On slide 64, then, a summary. What happens with a change in concentration? Will this shift the equilibrium? Yes, it will shift it. Will it change the equilibrium constant? No. What about a change in pressure? Yes, you will change your equilibrium, but it will be dependent on the moles of gaseous products and reactants. And so, no, you should not change your equilibrium constant. What about volume? Yes, that will shift in equilibrium. Again, the note is, remember, that's dependent on the number of moles of your gaseous products and reactants, but it will not change the equilibrium constant. Temperature. Yes, that will shift in equilibrium, and yes, it will change in equilibrium constant because equilibrium constants are temperature dependent. What about adding a catalyst? No, it won't shift the equilibrium. And no, it won't change that equilibrium constant. This is one of those charts you need to keep track of on those quizzes and tests.
Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. The word stress means a change in concentration, pressure, volume, or temperature. Click on one of the buttons below to view animation showing the effect of these stresses on a system at equilibrium. Iron 3 thiocyanate, which is FeSCN3, dissolves readily in water to give a red solution. The red color is due to the presence of hydrated iron thiocyanate ions, FeSCN2+. The equilibrium between undissociated iron thiocyanate ions, iron 3+ ions, and thiocyanate ions SCN- is given by this chemical equation. FeSCN2+ aqueous, which is red, in equilibrium with iron 3+ ions, which are pale yellow, plus SCN- aqueous, which is colorless. Click on one of the buttons to add sodium thiocyanate or remove iron 3+ ions from the solution. In this case, the stress applied to the equilibrium system is an increase in the concentration of thiocyanate, SCN-, from the dissociation of sodium thiocyanate. To offset this stress, some iron 3+ ions react with some of the added thiocyanate ions, and the system shifts from right to left to re-establish equilibrium. When the system shifts to the left, iron thiocyanate ions are produced, which have a red color. Consequently, the red color of the solution deepens as more iron thiocyanate ions, FeSCN2+, are produced. Note that the sodium ions are not shown in the simulation because they are spectator ions. Oxalic acid ionizes in water to form the oxalate ion C2O4 which binds strongly to the iron 3+ ions. Free iron 3+ ions are removed from the solution as the stable yellow ion iron 3 oxalate is formed. The system shifts from left to right to replace some of the iron 3+ ions. As the system shifts to the right, the concentration of iron thiocyanate ions, FeSCN2+, decreases. The red solution turns yellow due to the decrease in concentration of the red iron thiocyanate, FeSCN2+ ions, and the formation of the yellow iron 3 oxalate ions. Note that the reaction between iron 3+ ions and oxalate ions is not shown. The shift in the equilibrium position is the focus of the simulation. Consider the equilibrium between iodine gas molecules, I2, and iodine atoms at high temperature. Iodine molecules in the gas phase are a purple color, and iodine atoms are colorless. Under the given reaction conditions, the ratio of I2 molecules to iodine atoms is 2 to 3 at equilibrium, as shown in the microscopic view. Let's stress this system by changing the pressure. Click on one of the pressure buttons. You have increased the pressure by decreasing the volume of the container. The system can partially offset this stress by decreasing the moles of gas. Recall that pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, the moles of gas can be decreased if the system shifts to the left, producing iodine molecules and decreasing the number of iodine atoms, as you can see in the microscopic view. As more iodine molecules, which have a purple color, are produced, the color of the equilibrium mixture darkens. This can be seen in the macroscopic view. Note that the total number of gas particles has decreased from 10 to 8. You have decreased the pressure by increasing the volume of the container. Le Chatelier's principle states that this stress will be partially offset. The system can partially offset this stress by increasing the moles of gas. Pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, more moles of gas can be produced if the system shifts to the right, producing more iodine atoms, as you can see in the microscopic view. As more iodine atoms, which is a colorless gas, are produced, the color of the equilibrium mixture lightens, as you can see in the macroscopic view. Note that the total number of gas particles has increased from 10 to 12. Consider the following reaction at equilibrium. N2O4 in equilibrium with nitrogen dioxide, NO2. Under the given reaction conditions, the ratio of N2O4 molecules to NO2 molecules is 2 to 3 at equilibrium, as shown in the microscopic view. Because NO2 is a brown gas, the equilibrium mixture has a brown color, as shown in the macroscopic view. Let's stress this system by changing the temperature. Click to select either increased temperature or decreased temperature. You have increased the temperature of the system by adding heat. The Chatelier's principle states that this stress will be partially offset. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can partially remove the added heat by shifting to the right, producing more NO2 and decreasing N2O4, as you can see in the microscopic view. As more NO2, a brown gas, is produced, the color of the equilibrium mixture darkens, as you can see in the macroscopic view. You have decreased the temperature of the system by removing heat. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can replace some of the heat that was removed by shifting to the left, producing more N2O4 and decreasing NO2, as you can see in the microscopic view. As more N2O4, a colorless gas, is produced, the color of the equilibrium mixture becomes lighter, as you can see in the macroscopic view.
So slide 65, example 1510. Let's consider N2F4 forming 2 moles of NF2. This is an endothermic reaction because delta H is positive. Predict the changes if you heat in A, if B, if you remove some of the reactant, in C, if the pressure is decreased, and D, a catalyst is added. Slide 66 then. What should we think about when we're doing this problem? Sign of delta H means we're endothermic. With the removal in B, what happens if we remove some reactant? Will that increase or decrease QC? Letter C, how would the decrease in pressure change the volume of the system? And D, what is the function of a catalyst? How does it affect a reacting system? Not at equilibrium or once you are at equilibrium. Slide 67 for part A then. The stress applied is you added heat. So if you're going to increase the amount of heat, then being an endothermic reaction, this reaction will try to shift to decrease the amount of heat. So when you think of heat as this reaction, you're going to try to decrease the amount of heat if you add extra. The system will adjust to remove this added heat and will move towards the right. On slide 68 then, the equilibrium constant again is Kc is given as the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients, and this will increase with increasing temperature because the concentration of NF2 has increased. You shifted towards the product, so you increase this amount of NF2, and you've decreased the amount of N2F4. The equilibrium constant is a constant only at a particular temperature. If you change the temperature, the equilibrium constant will change. In part B, the stress here is the removal of N2F4. That's a reactant. So if you remove a reactant, the system will try to make more reactants. So you will move from right to left until the equilibrium is reestablished. As a result, some NF2 combines to form more N2F4. So on 69 then, the comment is that equilibrium constant will remain unchanged in this case because the temperature was held constant. It might seem that Kc should change because the NF2 makes N2F4 and you're removing some N2F4, but the system will adjust to replace only some of the N2F4. So the overall amount of N2F4 has decreased. In fact, by the time this equilibrium is reestablished, the amounts of both NF2 and N2F4 have decreased. Looking at the equilibrium expression, we see dividing the smaller numerator by the smaller denominator will give you the same value of Kc. Slide 70, part C. What if you decrease the amount of pressure? So if you decrease the amount of pressure, the system will try to increase the amount of pressure. But what we also saw was that since P is down, V would be up. So the system will adjust to remove the stress by increasing the pressure. Pressure is directly proportional to the moles of a gas. So in a balanced equation, we see the formation of NF2 from N2F4 will increase the total number of moles of gas. You have 2. So that will increase the pressure. Therefore, the system will shift from left to right. You will go from left to right to reestablish this equilibrium. The equilibrium constant will remain unchanged because the temperature was held constant. Part D on slide 71, again, what's the function of a catalyst? Well, it will increase the rate of the reaction. So if a catalyst is added to a reacting system that's not at equilibrium, the system will reach this equilibrium faster than if it was left undisturbed. But if you are already at equilibrium, as you were in this case, the addition of a catalyst will not affect either the concentrations of the NF2 or the N2F4 or Kc. The end.